Okay, so keeping up the or keeping the blah blah. Okay, keeping the ball rolling for chapter 13. We're going to talk about UV vis spec stuff, and so UV spectroscopy is basically when we shoot a molecule with high energy beams, and we are going to check the absorption. And so the absorption is going to tell us the level of conjugation we have in our molecule. So the more conjugation means the lower the energy, which means lower frequency, which means we are absorbing a higher wavelength. Dr. West will probably go over, or he probably has gone over, like, what exactly UV spec is and how it works and all that stuff. All you really need is this. So if you know this, you're good to go. And then someone had asked, you know what? Yes, let me repeat this and then I'll answer the question in the chat. So basically, UV spectroscopy is we shoot a high energy beam and our molecule is going to absorb that beam, and then we're going to check the absorption, right? And all the absorption is going to tell us is the level of conjugation in the molecule, aka how many double bonds we have in conjugation. And so the higher the level of conjugation means we have lower energy, because we said more conjugated is more stable. And then lower energy is going to correspond to lower frequency and higher wavelength. And so conceptually, like, cool, if you know that, awesome. The way this is actually going to be applied and how you're actually going to have to ask questions is like, excuse me, is like these examples below. So he's going to ask you which one will have the longer wavelength, right? And we know that long wavelength, we know that long wavelength equals more conjugation. So what he's really asking you is which of these is conjugated. And someone already said it. This one. So our answer is number 1, because long wavelength equals more conjugation. So if this one is conjugated, what's this one? Isolated. Awesome. So since this one is isolated, it's basically garbage in comparison. So for the second one, it's saying which one will have lower energy. And we know lower energy equals more conjugation. Ta-da. And we have so much going on in these molecules, right? Like, they're big and huge and scary. But we can basically throw anything that's not a double bond in the garbage. So this is our conjugated area. This is our conjugated area. Right? And so since we're looking for lower energy, we're looking for which one of these two is the most conjugated. What do you think? Is it the one on the left or the one on the right? The one on the right, or number 2. I absolutely agree. And we know that it has a higher level of conjugation because it has 3 double bonds. This one only has 2. Okay. So this third question is saying which one will absorb a shorter wavelength. And so are we looking for more or less conjugated now? Less, exactly. So short wavelength equals more conjugated. Ugh, this looks really wonky, but that's fine. So, is this one conjugated, accumulated, or isolated? This one right here. Hold on. No, yeah, I'm just a doofus. You guys said less, and I said less, but then I drew the wrong arrow. That's my bad. So shorter wavelength equals less conjugated. You're right. And you guys are also right. This one is isolated. And what about this one? Is it conjugated, accumulated, or isolated?
I think that one may be conjugated because of the double bond on the O can have resonance.
Yes, and I totally agree with you. So this is one of those tricky ones, but you were totally right. So what we said is it's isolated if it has sp3, right? But as Paul, I believe, said, this is not sp3, it's sp2. So the conjugation will actually continue because of this double bond. So we could say this whole thing is conjugated. So, which one is the right answer to this question? The left or the right? Ooh, we got a little 50-50. Okay, cool. So, yes, it's going to be the one on the left because number 1 and 2 we're asking about most conjugated, excuse me, but short wavelength wants less conjugated. And so we know this one is isolated, so clearly it's the least conjugated one. Ta-da! So I will zoom out a tad so you can see all of this. And then while you guys are looking at that, someone asked me a question a million years ago about Diels-Alder reactions. And so yes, we will be covering Diels-Alder. For some reason, last semester I chopped the chapter 13 handout into 2 different handouts, and I think that was because they were covered on 2 different exams. I forgot I had done that, so I'm just going to go ahead and put them together in one handout and then re-upload it for you guys. So I will do that today. I hope that answers your question. All right, so we went through this kind of fast, like in less than 10 minutes. So do you have any questions, comments, concerns, anything like that? If not, we can move on to the good stuff. Sorry, we're good. You guys can see and hear me now, right? Okay, cool. For a second, I didn't get a response, and I was like, oh no, what happened? All right, so I think that's a sign that we should move on. We kind of already talked about this on the last page, so we're going to skip it for now, and then we can come back to it eventually, maybe. All right, so I'm going to go ahead and do this on an extra page just because there's definitely not enough room for me to do everything I want to do on this page. But then I will come back up here and we can fill this out together. So, yeah. All right. So this stuff, I'm not going to lie to you, is a lot to draw. And it does tend to be kind of confusing. So I will send you guys like this page that I'm going to do as like a PDF. So if it's hard for you to like write and also pay attention at the same time, I would highly recommend you guys just watch and pay attention and then go back and write things at the end. That's just my personal like tip, but again, you can do whatever you want, you know. But okay, so when we are doing molecular orbital theory, we're going to focus mainly on 1, 3 butene, or I think that's what he tends to call it. So 1,3-butadiene basically just means that we have 1, 2, 3, 4 butene, and we're going to call it a diene because we have 2 double bonds. Diene, 2 double bonds. Okay. And 1,3-butadiene is going to be kind of our base molecule. So we're going to do this in the ground state, and then we're going to do this in the excited state. And I'll tell you what that means in a second. So we are going to talk about atomic orbitals. We're going to talk about molecular orbitals. And we're going to talk about pi electrons. So when we draw our orbitals, I'm going to go ahead and draw them in red. And they're kind of wonky, but you get the point. So in each one of these orbitals, we know we have a double bond, right? So how many pi electrons will there be in each one of these p orbitals? Okay, so someone asked me to like restate the question. So each of these orbitals is a p orbital, and we know that p orbitals are what make the double bonds. So if each of these has a bond in it, how many electrons do we have in each orbital? 1. Awesome. So I'm going to draw the electrons in blue. And you guys told me that there's 1 double bond. 1 per double bond. So I'm going to do this to show you that those blue electrons are each part of a double bond. Did I lose anyone yet? I know it's really funky to look at. If at any point you feel completely lost, let me know. Someone said not yet. I feel that. Okay, so how many orbitals do we have drawn here? 4, exactly. So we have 4 atomic orbitals. And we're going to say that that correlates to 4 molecular orbitals. I'm sure Dr. West talked a lot about orbitals. So here, all you need to know is we draw 4 p orbitals. That means we have 4 atomic and molecular orbitals. And now, how many pi electrons do we have? Oh, it's the same answer as before, so I didn't notice that people were answering. Yes, it's 4. Awesome. So we have 4 pi electrons. Perfect. And we know that the pi electrons are the blue ones. And so now we're going to draw our molecular orbital diagram. And these 4 orbitals are going to correspond to these lines that I'm drawing. So each of these orbitals corresponds to one line. And we are going to number these orbitals pi 1, pi 2, pi 3, and pi 4. We can also call them psi 1, psi 2, so on and so forth. That means the same thing. I know Dr. West sometimes does one or the other, so I just like pi, so we're going to stick with that. So now that we have pi 1, 2, 3, and 4, we are going to fill in our electrons. So we have 4 electrons, and we have to fill up one energy level before we can go up to the next one. So we're going to do 1, 2, 3, 4. Alrighty. Anybody confused yet? If you are, that's totally valid, but I just want to make sure nobody's lost at any point. So, okay, someone asked a great question. They said basically, I thought it was 1 electron per orbital, and you are totally right. So each one of these orbitals only has 1 electron, but these orbitals are now corresponding to energy levels. So we're going to basically say that this is an atomic orbital or a molecular orbital, and it's going to correspond to these energy levels. And so each energy level has 2 electrons. So someone said, what's the difference between atomic and molecular orbitals? I'm going to save that question, and we're going to talk about it at the end because it's not super important. You're not going to be asked about it or anything, and it's kind of a long story. So if we get through everything, I will go back and talk about it. If not, I will send you an email about it. Is that fair enough? Okay, cool. So now that we have put the electrons in their place, we are going to talk about bonding versus anti-bonding orbitals. So there's 2 ways you can explain this. And I'm more of a fan of the Rosemary simple way, but I will tell you both ways. So how I like to think about it is we take the number of energy levels, and here we have 4, right? And you always have to have the same number of bonding and anti-bonding orbitals. So we're always going to just take this and cut it in half, and anything below the half line is bonding, anything above the half line is anti-bonding. So we draw the yellow line. Anything above the yellow line is anti-bonding. Anything below the line is bonding. And just to reiterate, so we always have to have the same number of bonding and anti-bonding orbitals. They always have to correspond to one another. So I always take it, cut it in half, and say anything below is bonding, anything above is anti-bonding. And yeah, someone answered the question in the chat, a super simplified version, and they basically said, for the purposes of this class, they're essentially the same thing. So the number of atomic orbitals is basically always going to equal the number of molecular orbitals for this class. So that is absolutely true. Thank you for saying that. Okay, so a fun way that we denote antibonding orbitals is with a star. And so we're going to go ahead and give a star to pi 3 and 4. So we know that it's antibonding. And then someone said, just to reiterate, antibonding has to equal bonding. Yes, so there has to be the same number of bonding and antibonding orbitals. Okay, so we're going to go one more step, and we're going to name something called the HOMO and the LUMO orbitals. And I'm going to write down here, I will make these in purple because I like purple. So the HOMO is the highest occupied, oh god, that's so ugly, molecular orbital. And then the LUMO is the lowest unoccupied molecular orbital. Essentially, HOMO is the highest level that has electrons. LUMO is the lowest level that does not have electrons. So, pi 2 is the highest number with electrons in it. So we're going to say this is the HOMO. And pi 3 is the lowest empty orbital. So I'm going to reiterate that just because I stuttered a little bit. So pi 2 is the HOMO because it's the highest energy level with electrons in it. And pi 3 is the LUMO because it is the lowest energy level that is empty. So we're going to say LUMO. So, at this point, is anyone completely lost? And someone in the chat said, like, aren't antibonding orbitals ones that appear because electrons have to push through something? So, you're kind of sort of onto it, but we're also not going to talk about, like, the actual, like, details of what antibonding is, because then you have to draw the bonding diagram and it looks very frightening. So there is a lot to it, and you are kind of right, but for the purposes of this class, just know that antibonding has to correlate to bonding. So like pi 1 correlates to pi 3, pi 2 correlates to pi 4, and like the electrons are going to move up if excited. So yeah, we're going to leave it at that. And someone asked me to repeat the HOMO-LUMO thing one more time. So yes. So the HOMO is basically the highest energy level that has electrons in it. And the LUMO is the lowest energy level that is empty, right? And then someone said they have to go. Yes, this will be uploaded today. Bye-bye. Okay, so pi 2 is the highest number that has electrons in it. So we're going to call that the HOMO. Pi 3 is the lowest number that is empty. So we're going to call that the LUMO. And that's pretty much all there is to it. Any questions? So someone asked about non-bonding. We're going to put a pin in that and we'll get to it in like 5 minutes. Okay. So I forgot to put this on top. We're basically talking about the ground state right now. Okay. So I'm going to go up here and we're going to fill out the diagram together as promised. So how many Sorry, I lost it for a second. How many bonding molecular orbitals do we have in the ground state? 2. Absolutely. Okay, so how many bonding electrons do we have in the ground state? 4. And you might be thinking, what is a bonding electron? So, a bonding electron is any electron that is in a bonding orbital. And someone asked, how do we know that there's 2? So basically, we knew that there's 4 orbitals. We cut it in half. 2 of them are bonding. 2 of them are anti-bonding. And we know all the electrons are in the bonding orbitals. So we put 4 here. All right, so how many anti-bonding orbitals do we have? 2. How many anti-bonding electrons do we have? 0. And someone just went, dude, I finally got it. And that made my whole entire day. Thank you for that. Okay. And did we talk about non-bonding? No. So we're just going to go ahead and say 0, 0. We didn't talk about non-bonding yet. Cool. So, on a scale of 1 to 5, 1 being you have absolutely no idea what's going on, and 5 being like, yeah, this is cool. I got it. No questions asked. How do you guys feel? Someone said 8, and so, hell yeah, dude. Okay. I'm sorry, I don't mean to be teasing. Okay, someone said 2.5, someone said 3.5, someone said 3.8. I appreciate that answer. That's very well thought out. So no one's like, well, one person said 1, and so we're gonna work on that. I got you. But for the most part, everyone has at least some idea where we are, which is awesome. Okay. And someone had, and then someone said they only put 1 because they had to leave for a minute. That's fine. we got you. We'll fill in the gaps. And then, okay, so someone basically asked, how did what I drew on the left correlate to what I drew on the right? And basically, all right, so here we have our atomic orbitals, right? These are just the orbitals that we have in our actual molecule, right? These are the p orbitals. Obviously, there's a bunch more orbitals that I didn't draw out because that would just be too complicated. All we need for molecular orbital theory is our p orbitals and pi electrons. So for MO theory, all we need is p orbitals and pi electrons. So that's all I have drawn. So altogether, we have 4 p orbitals. And since there are 2 double bonds, each of these p orbitals have 1 electron inside them. And so they have 4 pi electrons. So that's all we need from this. This is our actual molecule. That's what it tells us. And someone said, like, just to clarify, every carbon has a p orbital. And yes, okay, here's a little, like, asterisk there, right? Every sp2 carbon has a p orbital. So anything that's sp2 hybridized has a p orbital. And I will make this a cute little note on here. Nope. Sorry, I decided I had to do this, and now I'm very intrigued. How do I add something? Okay, I'm sorry. That was unnecessary, but it was kind of fun. Okay, so we're going to talk about what has a p orbital. sp2 hybridization. And sp2 includes double bonds. It includes anions, so negative charge, cations, so positive charge, and radicals, which are one single electron. So all of those are going to have p orbitals. So it's not like every carbon ever, but every carbon that has a double bond, an anion, a cation, or a radical. So if you want a screenshot, write this down, whatever. And then we're going to chill, dude. Chill, bruh. Okay. So now that we understand the left side, we are going to basically take the number of atomic orbitals and we're going to draw these molecular orbitals. So each of these corresponds to one energy level, right? And so once we have our 4 energy levels based on these 4 orbitals, we're going to go in and fill in the electrons. We have 4 pi electrons. So we start going 1, 2, 3, 4. And someone pointed out there's only 1 electron per orbital here. Why is that different here? Well, that's because each of these is only really capable of holding 1 because it's double bonded, right? Versus here, we're talking about energy levels. So each energy level can have 2 electrons. And we know that we have to complete one energy level in order to move on to the next one. All right, so basically we're done with the left side. We can cover that up, right? We know that we have 4 energy levels, and so we have to break down which one is bonding and which one is anti-bonding. And we know that we have to have the same number of bonding and anti-bonding orbitals. So we're just going to cut a line in the middle. Whatever's under the line, is bonding. Whatever is above the line is anti-bonding. And so that's kind of how we set everything up. What if it's odd? You just really want to get to the non-bonding. We will talk about that in 1 second. So if it's odd, it's going to be non-bonding. And that tends to really, really confuse people. So I want to draw it out before I talk about it. No, that's okay. Don't ever apologize for wanting to know more. I just really don't want to confuse anyone. So can I say that again? Which part? Because I really do want to move on, but I don't want anyone to be super confused. But this is recorded and it will be posted right after, so you can go back and watch it. But yes, okay. So now, if we go on to the excited state. Does anyone know what happens when it gets excited? Something moves up. Awesome. So I'm going to go ahead and do like a red arrow. And we're going to say that when something is excited, 1 electron from HOMO goes to the LUMO. And someone actually said that in the chat, so good job to you. So yes, when something is excited, 1 electron from the HOMO is going to go into the LUMO. So I'm basically going to copy and paste this diagram because mostly everything is going to stay exactly the same. All right, so all we're going to do is move one electron. Please chill. There we go. From the HOMO to the LUMO. Okay. So, now that there's an electron here, do we have to change the HOMO and LUMO? Because remember, it means highest occupied and lowest unoccupied. So are we going to change the names? So a couple people said yes, right? Because that's kind of obvious. That makes sense. But no, it's not going to change because chemists hate us, right? No, I'm kidding. So how I like to think about it is think about all of these orbitals like baskets, right? And so we have 4 baskets, right? And we're going to put our like bouncy balls in there. And each electron is a bouncy ball, right? So we like to keep track of our bouncy balls, so we label each of our baskets. And so this basket is pi 1, this basket is pi 2, this basket is pi 3, and this basket is pi 4, right? And we know that pi 2 and pi 3 are special baskets, so we put a special HOMO sticker on it, and we put a special LUMO sticker on pi 3, right? So now we have our 4 baskets. We're going to throw 2 balls in here and 2 balls in here. Awesome. And so now for a second, we have a lot of energy, and one of the balls jumps from this basket into this basket, right? But this bouncy ball does not belong in this basket, so it's not going to stay here forever. As soon as we calm down what's going on in the room, we're going to pick up the bouncy ball and we're going to put it back in this one. We're not going to go and like change the name of things, because in order to change the name, you have to like pull off the sticker and put it on the other basket, right? That's dumb. So instead, we just pick up the bouncy ball and we put it back. Some of you might have thought that was a really stupid way to explain it, but I know this helps a lot of people. So think of it as kind of like baskets and bouncy balls. So when it goes to the excited state, we accidentally just moved our bouncy ball. We're not changing the label of anything because our baskets are not changing. We're just moving how many balls are in each basket. So with that in mind, I'm going to zoom out, but if you guys can't see it, we can zoom in a little bit. So let's answer our questions. In the excited state, are the baskets changing? Yay or nay? No. Okay. So the number of bonding orbitals is still 2. And the number of antibonding orbitals is still 2. But now, how many electrons do we have in bonding orbitals? 3. And how many electrons do we have in our antibonding orbitals? 1. Absolutely. And we still didn't talk about non-bonding, so 0. We ignore that. Okay. So now we're going to do a little check-in again. 1 is I have absolutely no idea what's going on. 5 is I'm a pro. I know this perfectly well. How do you guys feel? 3.99. Hell yeah, dude. 4.2. We love to see it. I love how much thought you guys are putting into this. Okay, cool. So most of us feel pretty good. No one has said a 1. And if you feel like you're at a 1 but you don't want to say it, that's okay too. But hopefully it's clicking. Some people are saying it's slowly clicking. Okay, cool. All right. So we are technically done, but this is an extra session anyway, so I'm just going to go ahead and keep going until we're done with molecular orbital theory. If you guys have to go, I totally get it, but I'm just going to keep blabbering, and you can watch this again afterwards. All right, so now we have those pesky allylics and non-bonding orbitals and all that garbage, right? And so I'm going to start out with the anion, and then I'm going to do the radical, and then I'm going to do the cation. I hope that's the order I gave you up here. Nope, I gave you a random order. So we're going to do this one first. We're going to do this one second. And we're going to do this one third, just so every time we add 1 electron. And you'll see what I mean in a second. So going down here, let's draw a line. And now instead of a butane, we're going to have a propane. And we're going to have 1 double bond. And we're going to have a plus charge. So this is our allylic cation. And so first things first, we're going to figure out the number of atomic orbitals, molecular orbitals, and pi electrons. And bam, bam, bam. As we keep going, my orbitals get uglier and uglier. You got to get used to it. And so now, how many electrons do we have in each orbital? Okay, so some people said 1. And yes, there's going to be 1 in each of these orbitals. But how many electrons will be in this one? 0. I totally agree, because we have a plus charge. So there's going to be nothing in there. It's going to be empty. So how many atomic orbitals do we have? 3. Sweet. How many molecular orbitals do we have? Because those are the same. Yep. And how many pi electrons do we have? 2. Awesome. All right. So now we are going to turn this into the energy level diagram. And now we are going to have only 3 energy levels. But wait! What are we going to do when we have to cut it in half, right? So we have pi 1, pi 2, pi 3. And I told you that in order to figure out what's bonding and what's anti-bonding, you cut it in half. So we know what's above the line is anti-bonding. We know what's below the line is bonding. So what happens when we have something on the line? What do you guys think? Someone said, do we just abort the second pi? Kind of. Not really. We're going to call it a non-bonding. So non-bonding orbitals, are going to come about whenever we have an odd number of orbitals. Because, again, we have to have the same number of bonding and anti-bonding. So when we have an odd number, the one that's left over in the middle is going to be non-bonding. And as we said last time, antibonding gets a little star. Non-bonding doesn't get anything special. Okay. So now I believe someone asked a question about how we put the electrons in there. It flew away, so I don't know what exactly it was. But when we put the sorry, my dog hit my door and it scared the crap out of me. Okay, so when we're putting the electrons in, we go 1 here. And then we know we have to finish up this energy level before moving on. So our second electron goes here. And that's it. That's all we have. So which one of these orbitals is going to be the HOMO? Pi 1, I agree. Because it's the highest number that has electrons in it. So which one is going to be the LUMO? Okay, we got a couple different answers. Someone said 2, someone said 3, someone said maybe there isn't one. So the non-bonding kind of trips you up, right? But when we're talking about our baskets, right, we're going to put the LUMO label on the first empty basket, right? And this is the first empty basket. So that's the one that gets the LUMO. So the non-bonding isn't going to affect HOMO and LUMO. HOMO is still the last basket that has electrons in it. LUMO is still the first one that has no electrons in it. So does that sort of kind of make sense? Yes? Okay. Good, good, good. So let's go ahead. And at this point, I don't think there's any way for me to show you this and also fill in the basket. Fill in the table. So take a look at this and then we'll fill out the table. And then someone said their Wi-Fi glitched. Yes, LUMO was number 2. And that's because LUMO is the empty one. So yeah. Okay, so that being said, let's scroll up. And remember, we did this one, so it's out of order. We're doing the cation first. And so how many bonding orbitals did we have? One. Yes. How many anti-bonding orbitals did we have? One. I agree. And how many non-bonding orbitals did we have? One. Yes. Also, someone just said, like, hello in the chat, so I assume that might mean your mic, like, I can't hear you and you're trying to talk. If that's the case, let me know. Oh, Wi-Fi glitch? Okay, cool. Never mind. Moving on. So, yes. So now we're going to go in and fill the number of electrons. So how many bonding electrons do we have? Someone said it's my Wi-Fi. So that's entirely possible. I am clearly home today. And so everything's a mess. But thank you for, like, sticking with it. All right, so yes, we have 2 bonding electrons. How many anti-bonding electrons do we have? 0. Yep. And how many non-bonding electrons did we have? Remember, we're talking about electrons? Yes, 0. Cool. And remember that this is in the ground state. So we're talking about the ground state here. All right, so let's scroll back over here. And just for funsies, let's also do the excited state. So again, I'm going to pretty much copy. And what is the only thing that's going to change? The electrons, yes. And specifically, we're just going to move one of these electrons up to the LUMO. So everything stays the same, but now we have one non-bonding electron. So someone asked a question. This is entirely my bad. Since they're the allylic radical anion and cation, there is supposed to be a double bond. I don't know why it's missing, but it'd be like that sometimes. All right, so next we are going to do the radical. So let's scroll back down and let's draw the allylic radical. Bam. Alrighty, so a lot of the things are going to be the same. So bam, bam, bam. How many electrons do we have in the first two orbitals? One each, yes. And then how many do we have in the last orbital? Yes, 3 total, exactly. So since we have a radical, I'll erase the black dot, but we're going to have 1 electron here. So we have 3 total. You are right. So atomic orbitals, how many do we have? 3. Molecular orbitals, how many do we have? 3. Pi electrons, how many do we have? Ooh, so we got some 2 and some 3. So since we have these 2, right, they're part of the double bond, we have at least 2. But this one is going to count as a pi electron. So if we have a radical, we will count this 1 pi electron. So altogether, we will have 3. So cation is empty orbital. Radical has 1 electron. So now we have 1. That's going to bother me a lot. 1. Why won't it make straight lines? 2, 3. Okay, cool. And just like we did with the last one, we got pi 1, pi 2, pi 3. So, based on what we just talked about, pi 1 is going to be what type? Pi 1 is going to be what type of orbital? And like what type, I mean like what are we going to name it? Bonding. Yes. Cool. So, bonding. What about pi 2? And then someone asked a question. I see your question. I will respond to it in 1 second. I do want to finish this thought, though. All right, and so then pi 3 is going to be... anti, yes. So it's anti-bonding. Wow, that's super ugly. Ta-da! Okay. So someone had asked... even though the radical isn't part of a double bond, it's still going to count as a pi electron. So yes, we're going to scroll real quick back to this handy dandy note. So p orbitals and pi electrons are anything sp2 hybridized. So double bonds, anions, cations, and radicals. So every double bond has 1 electron that's going to count per orbital. every anion has 2, every radical has 1, and a cation has 0. So the same rules apply. But I'm glad you asked that because there were probably other people who were also confused. So we're just going to scroll back down. Too far? Okay. So now that we have 3 pi electrons, we're going to do 1, we're going to do 2, and we're going to do 3. Gasp. Okay, now this looks a little bit different because we only have 1 electron in the non-bonding orbital. Did we do something wrong? Because this looks funky. Yep, so it looks weird, but we are still good. It's still correct. Everything is still good to go. So now, when we name the HOMO and the LUMO, this is where people get a little bit confused. So which one of these do you think is the HOMO? Okay, so we kind of got a 50-50 split. Some people said pi 1 and some people said pi 2. So remember, HOMO stands for highest occupied, and LUMO is lowest unoccupied. So LUMO has to always be the empty one, but HOMO does not have to be completely filled. It just has to be the highest number that has an electron in it. So in this case, pi 2 is half full, but it is the highest number that has an electron. So for that reason, pi 2 is going to be the HOMO. And since pi 3 is the lowest number that's empty, that one is going to be the LUMO. So I know it's a little bit weird compared to the ones we did before, but does it make sense a little bit? Sort of, kind of, maybe? Yes? Okay, cool. So I'm going to give you guys like 30 seconds because I'm freezing and I want to put on a jacket. And I want you guys to figure out where the electrons go in the excited state. So I'm going to give you a couple seconds to just think about that, and then we'll do it together. Okay, so we are back. And let me just write on here so nobody gets confused. This is the ground state. And so in the excited state, pretty much everything is going to stay the same. So just like before, I'm going to copy and paste the diagram. And what I want you to tell me is what electron are we moving where? Okay, so one person said we're going to move 1 electron from pi 2 to pi 3. Does everybody agree? I'm sorry, that's not funny. But someone just said no idea, and someone else said maybe at the same time, and that just really killed me. Okay, so yes, I agree, because remember, every time we excite the molecule, we have 1 electron jump from the HOMO to the LUMO. So nothing else matters. Whenever we're doing excited state, you have to move HOMO to LUMO. And so that's what we said. HOMO to LUMO. And I know it looks funky because someone said, is that empty energy level okay? So it's not very stable at all. But remember, this is just a temporary state. It's going to move back down. So it is okay if we have an empty orbital for a second. Alrighty, so we're going to do a check-in again. Now that we did the radical, 1 is now I'm completely lost, and 5 is I feel good, I know everything, good to go. How do you guys feel? Ooh, okay, so we're in the 4s. We're in the 4s. I'm very happy to see that. We got a 4, a 4.1, a 4.2, and a 4.5. Swag. I'm okay with that. Very happy. Okay, cool. So, let's go back before we move on and actually fill in the table because I will absolutely forget to do that. So, we did this last one. And we're talking about the ground state when we fill this out. So, in the ground state, how many bonding orbitals did we have? One, I agree. How many antibonding orbitals did we have? 1, I agree. How many non-bonding orbitals did we have? 1, I agree. Super duper. All right, so how many bonding electrons did we have in the ground state? 2, I agree. How many antibonding did we have in the ground state? 0. I kind of tricked you by going in like the wrong order, but in the ground state, yeah, we had 0 antibonding, but we had how many non-bonding? I'm sure you can hear the bird screaming. Yes, so we had 1 non-bonding in the ground state. In the excited state, though, how many non-bonding did we have? 0. Yeah. And so how many antibonding did we have in the excited state? 1. Perfect. So the bonding is going to stay the same. The non-bonding and antibonding are going to do a little flip-flop when it's excited. So you guys are doing awesome. Okay. So last but certainly not least, we're going to have the anion. So let's draw this baby out. You have a negative charge. Anion. And I'm going to go through and draw the orbitals. And how many electrons do we have in these 2 orbitals? Gosh, guys, you're spoiling all the fun. No, I'm kidding. So yes, we totally have 4 total. Totally total. And we're going to have 1 each for the double bond. And the spicy part is really this last one. So this is the first time we're going to have 2 electrons in 1 orbital. And we know that we have 2 because of the negative charge. So as you guys said, in total we have 4 pi electrons. How many atomic orbitals do we have? Yes, 3. How many molecular orbitals do we have? 3. Super duper. Alrighty. So that correlates to 1, 2, 3 energy levels. So we got pi 1, pi 2, pi 3. Alrighty. So just like you guys did for the last one, I want you to tell me what kind of orbital is pi 1. Bonding. Yep. What about pi 2? Non-bonding. And what about pi 3? Anti-bonding. Okay. And so now I want someone to explain back to me, why in the world do we have suddenly non-bonding orbitals? How is this different than the butadiene? Yes, because now we have 3 orbitals, which is an odd number. Absolutely. And what's the second piece of that? So why is it important that we have an odd number? Yeah, essentially, so we have to have an equal number of bonding and anti-bonding. So if we have an odd number, we have to name one non-bonding. That was a weird way of saying it, but I think you guys get what I meant. Okay, so now we have 4 electrons. So we're going to do 1, 2, go up to the second energy level, 3, 4. So which one is the HOMO? Pi 2, I agree. And which one is the LUMO? Pi 3. Yep. And I forgot to give pi 3 his little star. Ta-da. Spectacular. So that's pretty much it. Okay, cool. We did that one really fast. I almost call this the home. It's not the home, it's the ground. Cool. And so if we excite it. Wow, I just can't write anymore. My brain has left the building. So if we put this into the excited state, what is going to change? Yes, the electron, but more specifically, yes, I agree. So 1 pi electron is going to go from the HOMO to the LUMO, aka from pi 2 to pi 3. Super duper amazing job. So if I'll give you a second to look at this, and then we're going to go back up and fill in the table. All right. So in the ground state, how many pi orbitals do we have that are bonding? That was a weird way of saying that. 1. Yes. How many non-bonding do we have? 1. How many anti-bonding do we have? 1. Yep. Okay, so how many non-bonding electrons do we have in the ground state? 2, I agree. How many anti-bonding electrons do we have in the ground state? 0. How many bonding electrons do we have in the ground state? 2. Sweet. What if we're talking about the excited state? How many bonding electrons do we have in the excited state? 2. Yes. How many non-bonding electrons do we have in the excited state? Only 1. Yep. How many anti-bonding do we have in the excited state? 1. Perfect. You guys got this. Yay. Okay, so we're going to do a check-in one last time. How do you feel? Be completely honest. 1 is I have absolutely no idea what's going on still. I'm very confused. And 5 is I feel great. Okay, so 2 people said 5 out of 5. I am so proud of you. Some people are in the 4s. I am still so proud of you. And if anyone else doesn't want to say, that's completely fine. But whatever level you're on, I am very, 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 very proud of you. Hopefully, you know more than when you came in today. That's my biggest hope. And I know this is kind of complicated, so watch it one more time, kind of look at what we did, and if you have any questions whatsoever, please let me know. And I will send you this as a PDF. If I don't do that by the end of the day, someone send me an email and remind me, because I'm just very not here a little bit. You're very, very welcome. Thank you guys for sticking around. If you didn't do the attendance thing, I honestly don't even remember if I sent it. I'll send it one more time. But yeah, we're going to call it a day. Have a wonderful day and a wonderful weekend. Bye. I'll stick around if anyone has any questions for like a minute or two. But yeah, have a good one.